We have the first example on the velocity of sound. So it's a good example that gives a combined where we need to know the velocity of sound in air and the velocity of sound in a solid. Let me read this. It says a person puts their ears on steel train tracks and hears a train coming from far away. Then they stand up and hear the train coming through the air 3.4 seconds later. So you first hear it by putting your ear on the steel train tracks. Then you get up and then 3.4 seconds later you time it. You hear the train through the air coming. How far away is the train? And if the train is going at 40 meters per second, how long do they have to get ready to rob the train? So I'm kind of making this like the old westerns. And this is how people used to rob trains. They would hear the train coming through the steel, and then they would hear it sometime later, and it would give them a ballpark idea how long it's going to take that train to get to them, how far away the train is. We're going to assume that the temperature in the air is 20 degrees Celsius, right? So it's going to give us a good example with this, okay? So what's going to happen here? Let's draw a picture. So we have here a train, and then the train is making sound through the steel train tracks, right? So then you are here, putting your ear here. So you hear the train, right? So the distance is d. So the velocity, so the distance is going to be the velocity of sound going to take to travel through the steel. It's coming toward you, right? So it's traveling at the velocity of sound in steel, and then it's going to take a certain amount of time for the steel, for the sound to get to you, right? But we don't know that time. The only thing that we know is that afterwards you stand up, right? And then you hear that sound wave. So the sound wave is traveling through the steel, and the sound wave is traveling through the air, right? So we'll just write it like this. So it's traveling through there, but it's traveling much slower, right? So the distance here, the distance that it is from here to here is equal to the velocity of sound in air, but the time that it's taking through the air is equal to this t plus what? 3.4, right? The two distances are equal to each other because the sound wave leaves the train at the same time, right? It goes through the air and it goes through the steel. By the time that by the time the sound wave reaches you through the steel, the sound wave in the air is probably somewhere here. We don't know where it is. It's not necessarily halfway. It's probably even closer. So it's probably here. So when the sound wave reaches your head through steel, in the air it's still there. Then you get up and that's still going, that's still going, that's still going, and it takes from here to here was t, right? Because from here to here the sound took a certain time t. Then from here to here the extra distance, it took how many seconds? 3.4 seconds, right? To get to you. So then that extra time is 3.4. So we're saying this whole distance is equal to velocity of sound in air, t plus 3.4. We don't know the distance, but we can set these two equal to each other, right? Velocity of sound in steel, we calculated it in the theory section, right? Remember we did the Young's modulus of steel, we divided by the density of steel. And we got, for that, we got 4,984.4. So you put here 4,984.4 T. And then velocity of sound in air, well, if the temperature in the room is 20 Celsius, then you use that equation 331.4 square root of 1 plus T over 273, right? And then we already did that in the theory section, and then we got 303. Distribute the 343. We say 4984.4 T, 343.3 T plus 343.3 times 3.4. Then you can subtract this. You're gonna get. So what did this give you? This gave you the time that the sound wave took to reach you through the steel, during which time through the air it had gone from here to here, right? But we're not interested in that as much. The question asks what? The question asks, what's the distance from the train to you? How far away is the train? You see? So then we can take this t and we can put it into here, or we could put it into here. It doesn't matter. We should get the same answer. So you take this, put it into here, or put it into here. Well, putting in here is just easier. Just multiply this number by 0.2516. So take the number you got, just multiply it by the velocity of sound in the steel. So times 4984.4. So you get the distance is equal to 1, 2, 5, 3. The original distance of the train from you is, this distance in the picture is 1,253.6 meters, okay? So now, how long do you have after you get up and you hear it through the air? How long do you have to get ready to rob that train, right? So the velocity of the velocity of the train is given to you. Well, where's the train in this picture, all along this picture? So what we need to do is we need to add this t that we got to the 3.4, right? That's the total time that has elapsed, right? So t plus 3.4, that's going to be what? So the time that we got was 0.251496 seconds, right? Plus 3.4. This is the total time that has elapsed since the sound wave first began its path from the train to you, right? In that time interval, how far has the train traveled? So that means after you've heard it through the air already, and now you know the train is coming, right? And you can make an estimate how far away the train was originally. So this is the original distance. Original distance. Now we need to calculate how far the train is from you after you heard it through the air, right? So what's the distance of the train from you once you hear it through the air? Well, we need to take this distance and subtract how far the train has traveled during that time interval, right? We can draw this in a different color. How far has the train traveled? So during that 3.651 seconds, where's the train? So maybe the train is here. So how far has the train traveled? So that's we can call it d prime. So we take that distance and we subtract it from the original distance, right? So we have 1,253.6 minus d prime. So what is the velocity of the train? 40 meters per second, right? So you take 40, right? And then you multiply it by the total time that has elapsed. Now from the train to you, and you've already heard it through the air. Now you start getting ready, right? So then, how many seconds more will it take for the actual train to reach you, right? How many more seconds will it take? Well, all we need to do is divide this distance by the speed of the train, which is 40 meters per second, right? So 27.69 seconds. Right, 27.69 seconds. So you have almost half a minute to get ready to rob that train. This applies a couple of principles from the velocity of sound through the solid, velocity of sound through the air, and it applies it to a good problem. Okay? Thank you very much.